In this video, you will learn about the inverse trig integrals. Let's go ahead and review the inverse trig derivatives. Here they are. So the derivative of arc, we'll do arcsine first. And so the derivative of arcsine of u is going to be 1 divided by the square root of 1 minus u squared, and then times u prime for the chain rule. The derivative of arctangent will be let's see if you remember, it's 1 over 1 plus u squared, and then u prime for the chain rule. And then that last one is the derivative of arcsecant of u, and this is the weird one. And the derivative of arcsecant of u is 1 over, and then it's going to have a square root, and then there's two pieces. The first piece is the absolute value of u out front of the square root, and then it's going to be u squared on the inside minus 1, and then u prime for the chain rule. So remember that these are the three big ones. Remember that arc cosine, arc cotangent, and arc cosecant basically have a negative in front for those derivatives. Now we're going to do the integrals, and so as you imagine, the integrals are going to be taking this and going backwards, but we're going to integrate in a slightly different form. Here's what the inverse trig integrals look like. Don't write this down yet. Now, normally, so this is the regular derivative for arcsine, but when we integrate, we're actually going to replace that 1 with a squared. And the reason is it's easier to get it in terms of a squared than to turn any random number into a 1. And when we do this, this integral will end up being arcsine, yeah, there we go. And then the way we deal with this a is we do arcsine of u divided by a on the inside of those parentheses, and then we do a plus c at the end. So this is how you'll do the inverse trig integrals. You'll have to find both this a value and the u. So furthermore, a is always going to be a constant. And that's something you need to remember, is that when you are identifying the arc trig integrals, a is a constant, u is going to be variable. And this is similar to u substitutions, so the u's will have the x's in them when you do this. Let's look at the next one. The next one is arctan, and arctan, instead of being 1 plus u squared, it's going to be a squared plus u squared. And then we have the du for the integral, and this is going to be similar to arcsine. It's going to be arctan, and basically the way I remember these is each one gets one step more complicated. So we start with the same thing. However, arctan is one step more complicated than arcsine, and what we need is we need a 1 over a out front. And then don't forget plus c. And then the last one is arcsecant, and so we're going to do 1 over absolute value of u on the outside. We have that square root, and then we're going to have u squared, and instead of being u squared minus 1, it's u squared minus a squared du. And this is going to give us, okay, one step more complicated. So we're going to have 1 over a arcsecant, and u over a on the inside. And then the one step more complicated here is actually the absolute value, and the absolute value will go on the inside of arcsecant like that, and then we'll have our plus c. So these are the three integral forms for arc trig. For the inverse trig functions. Put these in your notes. This is how you'll see them in integral tables, etc. Let's figure out how to use them, because these are just weird looking. The first one we'll look at is an arcsine example. So let's say that we have the integral of 7 divided by the square root of 16 minus x squared dx. Alright, now I'm telling you that this is arcsine, but let's say you didn't know. What you would do is you'd say, okay, my integral does not have an x on top, and so I cannot do a u substitution. The u here would be 16 minus x squared, because that's the stuff inside. And so your du would be negative 2x dx. And the reason you can't do a u sub is because you cannot find this x on the top, so you can't do a u sub. So then you're like, okay, I can't do u sub. I have a square root in the bottom. So let's go back and look at the arc trig examples. And the ones with square roots are arcsine and arcsecant. But arcsecant has this absolute value of u on the outside, which we do not have in our thing here. There's nothing on the outside there. So it's not going to be arcsecant, it's going to be arcsine. The two things we need to figure out are we need to figure out the a value, and we need to figure out what u is. So if you remember, of course you remember, it's right here. Here's the arcsine formula. A squared is going to be that first constant term. So a squared is 16, so that means that a is 4. And I encourage you to rewrite the integral to look like this, 7 divided by square root, and write it as 4 squared minus parentheses, and what's the u going to be? The u is just going to be x. So if you're using different colors, great. Like, this will help you keep track of what's what. Dx. Alright, so a is 4, we've identified that, and then u is whatever is inside these parentheses. In this case, it's x. Oh hey, we are actually doing a u substitution here, so we need to find the du and doctor and counterbalance if necessary. In this case, du is dx, so we can just do the straight substitution. We'll get, the 7 is a constant, so I'm just going to pull it out, semi-permeable membrane style. So we get 7 integral of 1 over square root of 4 squared minus u squared du, and then this matches the arcsine form, and so I can just jump straight to the answer, which is 7 arcsine, and then looking back at this, okay, it's just arcsine of u over a plus c. And so all I have to do is just plug in the value for u, which is x, divided by the value for a, which was 4, like that, and then plus c, and that's my answer. So it's kind of a weird, you don't really feel like you're integrating because you're just plugging things into a formula, but it makes it nice because you don't have to think as hard. So yeah, that's how you do arcsine example. Let's look at another one. Let's say we have the integral of 1 over 16 plus 9x squared dx. Now notice, this can't do u sub because we have x squared in the bottom, and so that du would have an x in it, but we don't have an x on top. So that's always your first check. Can you do a u sub? In this case, we can't. So then we look at, oh, I have a quadratic in the bottom, but I don't have that square root. And so what I'm going to be looking at is, this is probably going to match the arctan formula because I don't have that square root. Alright, let's go look at it. So let's figure out what a is. Well, in this case, that 16 is going to be the a squared, and so when I rewrite this, it's going to be 1 over blah squared plus blah squared dx. So I would write it like that and then fill in the blanks. So the 16 will turn into 4 squared, and then check this out. The 9x squared, okay, obviously there's going to be an x inside, but it's not going to be 9x, because you have to remember that there's a squared on the outside of all of this. And so the 9, when it goes inside these parentheses, will become a 3. And so you can check, like, 3x quantity squared will get you the 9x squared, but you have to remember to take this constant term, the 9, and change it into a 3. So we have our a value, it's 4. We have our u value, which is 3x. And now we do our du, which is 3 dx. Oh, I need to do a little doctoring and counterbalancing, just like with a regular u sub. So I'm going to doctor with a 3 on the outside or on the inside and counterbalance with a 1/3. Now, this is going to match my arctan formula, so I'm going to do 1 over a. A is 4. I'm going to do my arctan of u, which is 3x, divided by a, which is 4. And I'm going to do my plus c, but then you also have to remember the doctor and counterbalance coefficient. That's going to come here too. So we're going to have a 1/3 and a 1/4, and so my final answer would be 1/12 arctan of 3x over 4 plus c. So again, you're following the formula, but you also have to remember there might be an extra fraction out here from any counterbalancing that you might do. Last one, everybody's favorite, arcsecant. Let's take a look at an example. Let's say we have 1 over x square root of 4x squared minus 1 dx. And so in this case, this will match arcsecant. Notice that the squared piece, the variable squared piece is first, and there's this piece that's variable on the outside. And so looking at arcsecant, this bottom piece, here you have that variable piece on the outside, and the variable piece is first inside the square root. Alright, let's figure out the u and the a. Let's go ahead and rewrite this as integral 1 over, I'll have absolute value of u, I guess we'll get there in a second. So we're going to have stuff squared minus stuff squared dx. Alright, let's figure out what a is. A is clearly going to be 1, because that's what 1 squared is 1. And then here, the u is going to be 2x. Ooh, that's interesting. So I have a as 1, and u is 2x. Now, I have this x here, but that's not going to match the u. And so what I have to do is I have to do like a doctor counterbalance before I actually do the du part. So what I need to do is I need to put a 2 down here, and then counterbalance with a, this is really 1/2 because it's on the bottom, so I need to put a 2 on the top on the outside. Now I can do the du, and so the du is going to be 2 dx. And notice here that, well, I have the dx, it's here. I need a 2 on the top, so I'm going to put a 2 on the top, and then counterbalance with another 2 on the outside. And so you have these 2's that are a doctor counterbalance pair, and these 2's that are also a doctor counterbalance pair. And notice that the 2's on the outside will eventually cancel, so we don't have to worry about them, which is nice. Alright, let's go ahead. We're just going to match the arcsine form, or sorry, arcsecant form. The arcsecant form is 1 over a is 1. We have arcsecant of the absolute value of u, which is 2x, divided by a, which is 1, and then plus c. Notice that my doctor and counterbalance coefficient was 2 over 2, which goes away because it's 1. And really what happens here is because even though there weren't absolute values here in the beginning, they show up in the end in the answer, so really don't have to worry about them. Just make sure that you do put absolute values in the end, the final answer. So hopefully this helps you solve these these inverse trig problems. We'll look at some examples of how to figure out which integration technique to use in a later video.